In this video, we're going to learn about the Pythagorean Theorem, how to use it to find missing side lengths of triangles, including when some of those sides are irrational numbers. So let's start just by connecting the dots with kind of our area model that we've used in the past. So we're going to draw a right triangle that has one leg of 3 and one leg of 4. And we're going to label it with our vocabulary. So I'm going to do mine kind of in the middle of the page because I'm going to be drawing a square off of the side of it. You might want to see what mine looks like before you do yours. And so this one right here, this is a leg, this is a leg, and then the diagonal side is the hypotenuse. And the hypotenuse is always opposite from the 90-degree angle, and the two legs make up the 90-degree angle. Okay? And now the Pythagorean Theorem says that if we square the legs, they'll add up to the area of the hypotenuse. So let's draw in those squares. So the leg of 3, that's going to give us a square with the area of 9. The leg of 4, that'll give us a square with the area of 16. And then the leg of 5, that's weird, but we did practice drawing some tilted squares in a previous video. So let's go ahead and go up 4, 1, 2, 3, 4, and then over 3, and draw that in. And that's a right angle, that's good. So now I'm going to go down 3 over 1, 2, 3, 4. There's another right angle, and I'll connect the last two to also make a right angle. And then this is hypothetically supposed to be 25. We can prove that it is by breaking it up into right triangles that we know how to find the area of. Right? Hopefully that feels a little bit familiar. So we have 1 in the middle, and then this is a 3 by 4, so half of it, so that's 12, so half that would be 6. So each of those triangles is the same. They're all 6. 6 plus 6 plus 6 plus 6, that's 24, plus 1 is 25. So what we just showed here is that the legs are always sides A and B. They're interchangeable, doesn't matter which one's which. And then the hypotenuse is always side C. So we have an A and a B, and then the hypotenuse is always side C. So if we take a formula, A squared plus B squared equals C squared, there we go. And then we plug in, the A is not the area, or the B is not the area, the A is that side length. So in this equation, A equaled 3, B equaled 4, and C, well, what's the square root of 25? C was 5. Even though it's that weird tilty length, it is 5. So we do 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. This is a true statement, right? And we can use this fact to solve for missing side lengths. So let's give it a try. Alright, so we're going to have a triangle with one side length of 5, one side length of 12, and then an unknown side length, and we're going to try and figure out what that would be. So we're going to decide where A, B, and C are. So we remember that A and B are always the legs, which are the ones that touch the 90-degree angle, that touch the right angle. So I'm going to say that 5 is A, 12 is B, that leaves X to be C, or the hypotenuse. I'm going to plug them into my formula. So 5 squared plus 12 squared equals x squared. You can leave it as c squared if you want, but since I said that side was x, then I'm going to put in an x for it. So that'll give me 25 plus 144 equals x squared. Notice I'm not drawing squares, right? That was just my little example. Because it's true. The whole point up here was that if I took the area of this and I took the area of this and I like mushed them together like they were clay, I would get the same area as the one of the hypotenuse. So then down here, I do this. This gives me 169 equals x squared. But I don't want x squared, right? I don't want this monstrous square that comes off the side of the x. I want the actual length. So I'm going to take the square root of both sides, because that's how I solve for a square. Take the square root of it, and that gives me the square root of 169 just happens to be 13. Amazing. Now, you'll notice both of the examples we've done so far, which were 3, 4, 5, and then 5, 12, 13, those were both what's called a Pythagorean triple. Pythagorean triple. There are lots more Pythagorean triples. So as you're working in this unit, as you come across, Pythagorean triple is 3 side lengths that are all whole numbers that make a right triangle. So usually it doesn't work out that way, right? Usually we end up with square roots. But sometimes we get beautiful ones like this that work. So as you run across them, you're going to make a little list of your Pythagorean triples to keep track. Now let's try one that's not a Pythagorean triple. All right, so I did not draw this one to scale, so don't bother counting the squares on my paper. You can just draw something that sort of looks like this. And so here, let's decide what's our A, what's our B, what's our C. The last two we were solving for C. Let's see if that's the same way this time. So A and B are the sides that touch the right angle. So 7 is A, and X would be B, and this time the 15 is going to be C. So that's different. So let's do our equation. So x squared, or 7 squared, plus 7 squared equals 15 squared. Doesn't matter what order you do those in, right? And that's weird. It's not on the side that we want, but that's okay. So I'll leave this as an x squared for now, plus 49, and 15 squared is 225. Your list of squares that's on your little cheat sheet here only goes up to 10. You might want to hand write in a few more, because you could very well use some that go up higher than that. And then I need x alone, so I'm going to subtract 49 from both sides. So x squared equals, and then 225 minus 49 gives us 176. And then we're going to take the square root of both sides. Now, 176 is not a square number. So, it no longer has the squared on it because I did the square root. Now, this is great and all, but I'm curious to see if this can be simplified. So what I'm going to do is I'm going to take my handy dandy calculator, or you could do it by hand if you're feeling like doing math by hand, and I'm going to test. I'm going to see, do any square numbers go into this? So I'm going to start at the top of my list here, well, except not 1, because 1 doesn't help, but I'm going to divide it by 4 and see what happens. I'm going to do 176 divided by 4. Oh, sure enough, it gives me 44. So I can simplify. This gives me the square root of 4 times the square root of 44. So that would be 2 root 44. Now, square root of 44, I can just look at that. I can see that's 4 and 11. So this is actually 2 times, let's show it out, times the square root of 4 times the square root of 11, which is 2 times the square root of 11. So this would simplify to 4 root 11. So my side length B over here is 4 root 11. Let's do another example. This time we're going to take a right triangle, looks like this. Pause, See if you can figure it out. So did you decide that this would be A, B, and C? So you should set it up as 3 squared plus x squared equals the square root of 39 squared. Kind of weird, huh? So that gives me 9 plus x squared equals, and then the square root of 39 squared, well, that's just like undoing that square root, right? So that's just going to be 39. So then I subtract the 9 from both sides, so x squared equals 30. Take the square root, and I get x equals the square root of 30. Now I can check it. Does 30 divide and simplify? So 30 divided by 4, 7.5. Didn't work. 30 divided by 9, 3.33. Well, I know it's not going to work because I'm going to get really small numbers now, right? So I don't need to check anymore. I know that this cannot be simplified. All right, and for your practice problem, I want you to find the missing side length. If we have a 10 by 2 right triangle, be sure to simplify your answer if possible.